Deep Dive. We sift through complex research so you don't have to, giving you the essential insights. Today, we're looking at the future of automation, particularly robotic manipulators. Those arms doing complex jobs in factories, surgery, even space.
That's right. Think automotive assembly lines, delicate medical procedures.
Mm-hmm.
These arms are everywhere.
They're incredibly sophisticated, but they face this huge computational hurdle, especially the really complex ones. It's called inverse kinematics, or IK.
IK is the fundamental problem, really. You know where you want the robot's hand, the end effector to be, its position, its orientation. The challenge is figuring out the exact joint angles needed to get it there.
And that gets exponentially harder with more joints, right? These high degree of freedom arms, maybe 7 joints like a human arm.
Exactly. The number of possible configurations just explodes. You're searching this massive, complex, nonlinear space.
And classical methods, like trying every possibility.
They just can't keep up. The complexity scales exponentially, something like OKN, where N is the number of joints. For a standard 7-joint arm, finding a collision-free path could take minutes, maybe even hours with older methods.
Which is just not practical. Not in a fast-paced factory, definitely not in surgery.
No way. That time lag kills the application.
Okay, so that exponential scaling is the bottleneck, and the focus of this deep dive is a really novel solution researchers are proposing. It's a quantum native framework, mixing quantum machine learning, QML, with Grover's algorithm. Sounds complex?
It is, but the core idea is powerful.
Yeah.
And the results we saw in the sources are pretty staggering. They're showing a quadratic reduction in that search complexity, basically turning an exponential problem into something much more manageable.
And the payoff.
Huge speedups. On actual quantum hardware, they got up to 93 times faster than standard classical optimizers as the problem got harder.
93 times? Wow. Okay.
Yeah, it's the kind of difference that makes currently impossible tasks suddenly feasible.
Right, let's unpack that. Before jumping fully into the quantum magic, why exactly do classical methods fail so badly, especially with lots of joints?
Well, the search space itself is inherently tricky. Classical algorithms, often things like gradient descent, they try to walk downhill to find the best answer.
Okay.
But these high-dimensional spaces are littered with traps. You've got local minima little dips where the algorithm thinks it's found the best spot, but it hasn't. And you have singularities points where the mass breaks down.
So it gets stuck easily.
Very easily. And then there's the topology. Even a simple 2-joint arm creates a configuration space shaped like a torus, like a donut surface. Navigating that, avoiding collisions, respecting joint limits. Classical solvers like Nelder-Mead or BFGS do it by trial and error, step by step.
And that trial and error just explodes computationally as you add more joints.
Precisely. That's the exponential wall.
Right.
They're trying to optimize, but the real problem is searching a vast, unsorted space. They aren't built for that scale of search.
Okay, that sets the stage perfectly. So how does quantum computing sidestep this? What's the fundamental advantage?
It comes down to superposition and entanglement. You take the robot's huge configuration space, all those possible joint angles, and encode it into qubits.
Right.
Now, because of superposition, a single quantum state can represent many configurations at once, instead of checking one by one.
You check them all in parallel.
Essentially, yes. You explore the entire space simultaneously.
And Grover's algorithm is the key to finding the right configuration within that massive superposition.
Exactly. Grover's is designed for searching unsorted databases. Classically, searching M items takes time proportional to M, so OM. Grover's algorithm does it in time proportional to the square root of MO squared CM.
That's the quadratic speedup.
That's the quadratic speedup. And when M is astronomically large, like the number of configurations for a 7DO arm, the square root is vastly smaller. The difference is transformative.
So it turns an optimization problem into a search problem that quantum computers are inherently good at.
You've got it. That's the core insight.
Okay, so the paper mentions this end-to-end pipeline embedded entirely in quantum circuits. That sounds important, avoiding shuffling data back and forth between classical and quantum.
Critically important. That classical quantum communication is a major bottleneck right now. Keeping it all quantum native makes it much more efficient.
So walk us through the stages. How do you translate a physical robot arm into qubits and then find the solution?
It's a 5-stage process, all integrated. Stage 1 is discretization and encoding.
Okay, what does that involve?
You have to take the continuous values, like joint angles, and turn them into discrete steps that qubits can represent. They decided to use 9 qubits for each parameter. That was a practical choice for today's NISQ noisy intermediate scale quantum computers.
9 qubits. How fine-grained is that? What does that mean for precision?
It gives you 512 discrete values per parameter. For angles, that translates to about 0.7 degrees of resolution.
zero point 0.7 degrees. Is that actually enough for precise tasks?
Surprisingly, yes. In their tests, that level of discretization was enough to achieve end effector positioning accuracy down to the submillimeter range, like 0.1 to 0.5 millimeters, which is actually really good, often meeting or beating industrial requirements.
Okay, impressive. So we've encoded the possibilities into qubits. What's stage 2?
Stage 2, QML for kinematic approximation. These are parameterized quantum circuit. Think of it like a quantum neural network.
QML, quantum machine learning.
Yep. They train this circuit, 1 QML, to learn the forward kinematics, how joint angles map to the hand's position. It learns the robot's movement patterns quantumly.
So the quantum circuit itself learns how the robot moves, avoiding classical calculations later.
Exactly. It approximates that complex function using quantum parallelism.
Okay, the system knows how the robot works. Now, how do you tell it what a good configuration is? The goal.
That's stage 3, cost Hamiltonian formulation. You translate the classical goal, like minimize position error, into a quantum object called a cost Hamiltonian.
Like in quantum physics.
Sort of. Think of it as creating an energy landscape across all the quantum states. Low energy states correspond to good robot configurations, high energy to bad ones.
So finding the lowest energy state means finding the best joint angles.
Precisely. And what's really neat is the flexibility here. It's not just position error.
Ah, yes. The paper mentioned other things you could minimize.
Absolutely. You can build Hamiltonians to minimize orientation error, maybe using something called Riemannian distance, or maximize manipulability, the robot's dexterity.
Make it more agile.
Right. Or minimize energy consumption, or crucially, build in collision avoidance by maximizing the distance to obstacles, all within this quantum cost function.
That's powerful, packing multiple objectives into one quantum search. Okay, we have the target low energy states. Stage 4 must be finding them.
Stage 4, Grover optimized search. This is where Grover's algorithm comes in. Use a quantum oracle.
An oracle?
Yeah, the oracle is a quantum routine that can instantly mark the states in the superposition that meet the low-cost criteria, say position error, below some threshold epsilon.
So it flags the good solutions within that massive parallel state.
Instantly. Then Grover's algorithm uses another operation, the diffusion operator, to amplify the probability of measuring those marked optimal states.
That's how you get the quadratic speedup, the amplification.
That's the core mechanism. It boosts the chances of finding the needle in the quantum haystack.
Okay, nearly there. We measure a quantum state. How do we get back to the real world?
Stage 5, classical verification. The quantum computer outputs a bit string. You decode that back into classical joint angles, Plawlers. Then you just quickly double-check using the standard analytical forward kinematics that the solution is physically valid joint limits. Hey, no obvious issues. It closes the loop.
A fully quantum loop, mostly. Very cool. Okay, theory sounds great. Let's talk performance. They ran this on actual IDM quantum hardware, right?
They did. And the results really highlight how the quantum advantage depends on the problem's complexity. It's all about that scaling.
So what happened with the simplest test case?
Case 1. A one-dome manipulator, just one joint, one link length to optimize. Here, quantum was actually slower.
Slower, how much?
Quantum took about 2.0 seconds. The classical Nelder-Mead optimizer, only 1.1 seconds. So quantum was about half the speed.
Okay, so that confirms the quantum overhead. Setting things up, managing the qubits. It takes time, especially for simple problems where classical is already fast.
Exactly. The overhead dominates when the problem isn't complex enough for the quantum speedup to kick in.
But then came the more complex case.
Then came case 2, the two-dome manipulator. 2 parameters, but crucially searching that tricky toroidal configuration space we talked about.
And how did classical methods fare here?
They really struggled. That exponential scaling hit hard. Nelder-Mead took 2100 seconds.
Wow, that's 35 minutes.
Yeah. Another one, BFGS, took 2600 seconds. Even particle swarm optimization, which is designed for global search, took 2200 seconds.
Yeah.
Basically half an hour or more.
Okay, the moment of truth. How long for the quantum framework?
22.5 seconds.
22.5 seconds compared to 2100 seconds.
Let that sink in. From over 30 minutes down to under 23 seconds.
That's the 93x speedup number.
It is the 93.3x speedup. It's a massive difference. And it perfectly illustrates the point. As the classical search space explodes, that quadratic quantum advantage just completely takes over and crushes the initial overhead.
Incredible. That really shows the scaling potential. Did they test anything else?
Yes, they did a multi-robot task. Case 3, dual arm grasping.
Ooh, coordinating 2 arms. That sounds complex.
It is. They optimized 4 joint angles across 2 virtual arms, trying to achieve a stable grasp on an object specifically, an antipodal grasp, where contact points are opposite. Requires minimizing error while meeting coordination goals.
And the result there? Still faster. Still significantly faster. The quantum framework showed a 9.4x improvement over a classical exhaustive search for this task.
So still nearly 10 times faster, even for a different kind of complex problem.
Right. It shows the approach isn't just a one-trick pony for specific topologies. It works for coordination, too.
Okay, looking at that pattern, slow start, huge speed up, then still significant speed up. What's the big picture takeaway here for robotics?
The takeaway is scalability. Classical methods hit an exponential wall. As robots get more complex, more joints, more dexterity, classical computation becomes the bottleneck for real-time control. This quantum-native approach, thanks to Grover's algorithm, offers a path around that wall. It provides a quadratically scaling solution for what is fundamentally a search problem. It makes real-time IK for complex robots seem possible.
So this work really builds a practical bridge between quantum theory and real-world robotics needs. High-precision tasks that were just too slow before. Exactly. It's not just the raw speed. It's the ability to find optimal solutions considering dexterity, energy, collisions in these incredibly complex non-convex landscapes. It enables a level of precision engineering that was previously computationally out of reach for dynamic tasks.
Okay, let's wrap up with a final thought for our listeners. The researchers stressed this works on current NISQ hardware with all its noise and limitations. So here's something to chew on. What happens when we get large-scale, fault-tolerant quantum computers? When that 93x speedup isn't just on a 2-to-1 problem, but applied to a standard 7-to-off industrial arm or something even more complex? What does that level of intelligent automation unlock for industry, for medicine, for exploration?
That's the billion-dollar question, isn't it? It could completely change the game.